Alright, so we have this question, and it's asking about to find the period of a pendulum. So we're told that we need to determine the period of a 1.7 meter long pendulum on the moon, where the free fall acceleration is 1.62 meters per second squared. So the clear difference here is that since this is on the moon, if it were on Earth, the acceleration would be 9.81 meters per second squared. But this is the moon, so it's not going to be that. It's going to be 1.62 as we're told. And that's because the moon is much less massive than the Earth is. So there's an equation we can use for the period of a pendulum. Just to be clear here, a pendulum, we're just talking about something fairly simple, whereas like some kind of weight on the end of a string, and that string has length L. Alright, so from here to wherever this is going to pivot about is going to be length L, and there's also going to be some kind of gravity pulling downwards on it, and the force of that gravity will be mg, but g, if it's on Earth, is 9.81, but in our case it's actually the moon, so it's 1.62. Alright, so that's the thing to keep in mind here. When we use our formula, we have to replace 9.81 with 1.62. Anyways, this weight, when you pull it from the center line, you pull it off in this direction, say, and then you release it, it will swing back and forth. And it will continue to do that, well, ideally forever, but in the real world there's friction and eventually it will stop. But we're not accounting for friction in this case. So it will swing back and forth forever if there's no friction. Actually, on the moon, it could probably do it for a fair bit longer than the Earth because there's no atmosphere to get in the way and slow it down. But it would still stop eventually. The string or the rope or whatever it is, itself would have internal friction, so that would still slow it down eventually, but it might go a little bit longer. So we know that the period of the pendulum, t is the period, is equal to, and let me show you this, period is equal to 2 pi times the square root of L over G. So it's 2 pi times the square root of L over G. And all we got to keep in mind here again is that G is 1.62, not 9.81. Let me see. So our numbers are given to us. Let's look at the units. 1.7 meters and 1.62 meters per second squared. So those units should work out just fine. Alright, so when we do that, let's look at what the units will do very quickly, first of all. So we're going to have the square root of a meter over a meter per second squared. And that's the square root of a meter times a second squared per meter, because you can flip over your fraction there. Meters will cancel out, and you'll get the square root of a second squared. So that's just going to be in seconds. So our period is an amount of time. In this case, it will be in seconds. And it's simply, the period, by the way, is the amount of time it takes this weight, once you let that fall, it will swing all the way across, and then back one time. And once it gets back to its original position, that's considered one period. Alright, let's go ahead and put this in a calculator. So it's 2 pi times the square root of 1.7 divided by 1.62. And that ends up being about 6.43 seconds. Alright. If we're going to use the correct number of significant figures, then our given data, the 1.7 only had 2 figures, so we should round off to 2. So this will be 6.4 seconds. And that's what your period for the pendulum should be. Just as a side note, one interesting thing about pendulums is that even as they begin to lose energy and ultimately it swings less and less until it stops, the period of that pendulum will actually be constant for that whole time. So you can actually, knowing what the period is, for instance, you can look at this formula and you can see the only thing it depends on is the length of the string and what the gravity is. And neither one of those will change, under normal circumstances. So that period of the pendulum actually will sort of tick back and forth, and one swing will always be the same length of time until it completely comes to a stop. So it might swing less and less and less, but it will also it won't move quite as fast at the ends of the swing. So what I'm saying is the time for one swing will remain the same until it comes to a complete stop at the end. So this is interesting because it actually means pendulums can be used as a fairly accurate way of measuring time, for instance. And of course, we've all seen like grandfather clocks and stuff that are based on this principle. If you have any questions about how I solve this problem, please feel free to ask. I wasn't trying to derive this formula or anything, so if you want to see that, I would be glad to show you, but it is a little bit more complicated. And if you have any questions, just feel free to ask, and I'll be glad to answer.